So, in this lecture we have seen one approach to derive the Kalman filter. So, what we did is that first we designed a weighted least square function, and then we designed the weight such that the estimator is minimum variance, standard optimization approach. Now, typically you will find that the Kalman filter is derived in two other ways, and these derivations basically originate from two major properties of what are known as minimum variance estimators. So, two major properties, one of them algebraic and the other based on probability theory. These two results are also used to derive the Kalman filter. Typically you will find in books. So, while we will not re-derive the entire Kalman filter, because that will involve another sequence of algebraic manipulations, but we will definitely look at these properties, because these properties are very important. They are very fundamental properties of the filter, and we will remember that utilizing these properties, that is, if we try to construct an estimator which will satisfy these properties, we will again arrive at the same equations and the same Kalman filter. So, that is why we need to review. So, first property, we will start with the algebraic property, which says that, which is some sort of an orthogonality property. We have also encountered this property for in the previous case, previously when we discussed the FIR filters for predicting the output. So, suppose the idea is that suppose if we have some measurements, okay. So, we are not right now saying that they are measurements, we are saying that suppose we have some random vectors W, and now based on these random vectors we in some way we want to construct an estimator of a vector x. These random vectors x and w are related in some way. We are not right now concerned about that. All we are saying is that this estimate that I want to generate, which I am here calling y, please do not confuse with the output y. In this case y is an estimate of x. So, I am trying to generate an estimate y of x using these w's, and not only using them. So, I am using all the w's from I equal to 0 to r, and I am not only using them, I am using them in a linear fashion, in the sense that this y is actually constructed by multiplying these w with constant matrices pi, which have to be chosen in some suitable manner, so that this estimate is good. But it is a linear estimate, because I am multiplying each of these w's. These w's are q dimensional, while these x's are n dimensional. So, we have to multiply this pi by n into q matrices. So, I am multiplying. So, basically multiplying a vector by another by a matrix means it is length scaling, either we are stretching the length and we are also reorienting the vector, right. So, we are basically, this is called a linear transformation. So, we are causing a linear transformation using only linear transformations from these w's we have constructed this y. This is my only constraint, that I am not using other nonlinear functions. Now if I do that, then the question is that using this sort of a rule, that is only using linear transformation, what is the best estimate that I can create in a mean squared sense. In other words, so now that sense will have to be defined. So I am now defining the sense here. So I have defined a quantity which I have denoted by these triangular brackets. Sometimes it is called an inner product, or so it is an inner product of these two vectors. One of them is n dimensional, the other is q dimensional. So right. So then this matrix becomes an n into q dimensional matrix. Okay. So it is, so this inner product is actually defined in this manner. So if you define this, it is nothing but the covariance of x and w, if you see this. So what is the trace of that covariance? It is what is the trace of this matrix? It is the actually this is a here defining trace will be difficult because it's an n into q matrix, but when you have trace of xk minus y, where this, so this xk minus y now, okay. So first let us give this definition of the inner product. Then if this w and x are of the same dimension, in other words, if we define xx or if we define ww, then this matrix will become square. If it becomes square, it will have diagonal elements. So trace means sum of diagonal elements. Okay. So what are the sum of diagonal elements of this xx? So it will be x1 minus expectation of x1 whole square. Next diagonal element will be x2 minus expectation of x2 whole square. Only the diagonal elements I am considering. So actually it is the variance of, it is the sum of variance of x1, x2, x3. This, when I say trace of this, I basically mean it is sigma I is equal to 0 to n xi minus expectation of xi whole square. This is the trace of xx. Similarly, trace of ww. Rather, yeah. So when I say, and this xx I define as this square. So when I say this, what I mean is, what is the, if this can be called as some sort of an error epsilon. So this is xk minus y is supposed to be an estimate of xk. So if you xk is the true state. So if you do xk minus y, you get the error. So if you take trace of this square, what you get is that you get the sum of squares of the, rather the sum of the variances of each components of this epsilon. So that is what I want to minimize. So I want to choose a y from this space y. This space y is the set of vectors y which can be generated by such linear transformation. Only from that set I must choose y, not from any other set. In other words, I must only use a linear estimator. So if I use a linear estimator, then what is that y which will minimize this? That I call my minimum variance estimate. So the minimum variance estimation problem says that determine such a y hat belonging to y, obviously, because each of these are generated from this. So obviously the minimizing solution will also from this. So find out that linear estimate which minimizes the sum of variance of the error squares. So that is a minimum variance estimate which has been calculated using linear transformations and using all the vectors wi. Okay. Now it turns out that this estimator has a very nice property. That is what we want to discuss. So what is that property? So the property is this, that if you actually happen to solve this problem and get this estimator y hat, then it turns out that the covariance of this error with respect to the will be orthogonal to the measurements, to all measurements, right. When this will be an n by q 0 matrix, this O means 0, that is each element of this matrix will be 0. So this is so in that sense the error of estimation, see you have constructed y using wj's. So it says that is the optimal estimate which after you, so you have sort of taken out all the juice or all the information possible from wj of xk. So now you have calculated some y hat, but still you could not get the full xk. So those errors are those that you cannot get from wj. So when can you not get anything from wj? When these errors become orthogonal statistically to wj, then you cannot extract any further information about those errors from wj. So these are sometimes called innovations. I mean, in a sense, I mean actually what they say is that the estimation error will become orthogonal to the measurements which have been used to generate the estimate. That is the whole idea. And this result is rather strong. This result says if and only if, which means that if you happen to generate this by some other method, this property will be satisfied. So if this is satisfied, this is satisfied. Not only that, it is the reverse also. So if you can somehow construct an estimator for which this is satisfied, then automatically this will also be satisfied. So it is both way implication. This implies this and this implies this. So if you can satisfy some estimator which will satisfy this, automatically the minimum variance property will be satisfied, right. So this is called a necessary and sufficient condition. By this IFF what we mean is if and only if. I don't know whether you have heard about this. So suppose this is a, logically speaking, suppose this is a clause A. This is some statement which is written in mathematical symbols. It is basically a sentence. So if that sentence is A and if this sentence is B, then what does this say? This say A if and only if B, which means that A if B and A only if B. So A if B means what? Means B implies A. If A if B, so if B is true, A is true. So B implies A, logically speaking, and A only if B means A implies B. Okay. So how do we prove this result? This is a very fundamental result of regarding the Kalman filter, because the Kalman filter is also a minimum variance estimate, as we have already seen, right. So for the Kalman filter this will be true. In fact you can, that is what I was saying, that in fact you can construct the Kalman filter by trying to construct an estimator for which this will be true, then automatically this will be true. So that is another line of proof or another line of derivation of the Kalman filter. So this is a, I mean I also told, I mean decided to discuss the proof because this is a proof by contradiction. I don't know whether you must have seen proofs by contradiction where you first assume that you assume that the theorem is wrong, and then you will arrive at some obvious fallacy like maybe the sun rises in the west. So then you will say that the sun cannot rise in the west, therefore the theorem is true. So I mean this kind of argument. So the idea is that you first assume that the theorem is wrong, and you can show that if you assume that the theorem is wrong, then you can arrive at some obvious contradiction, like I mean something like 1 is equal to 2 maybe, which is obviously wrong. So we are going to do that. Okay. So first we prove necessity. Necessity means we want to prove that if this is true, this is true. That is, this implies this. A implies B. We want to prove that. So we first say that let A not imply B, which means that this is true, but this is not true. Let us assume that first. It is a proof by contradiction. So we have assumed that let y is this whole thing, it's cumbersome to write, so I have called it fk. So let y is a minimizing solution of this fk, but let there exist some wj0, one of them, actually this should hold for all wj, j is equal to 1 to r, but let there exist at least one for which it does not hold. Okay. So if that is true, that is there exists some j0 where j0 belongs between 0 and r, this should be 0, such that this is not true, I am assuming. So then you have to prove that you have to then actually what we will show is that if that is the case, then obviously this cannot be the minimizing argument. In other words, we will show that under this condition we can find some other vector y, which is also linearly generated from wj0, but for which will give a minimum, which will give a value of fk which is actually less than that of y hat. So therefore y hat cannot be a minimizing argument. This is our line of proof. So what are we going to do? So our basic idea is that, so naturally if this is not equal to 0, obviously this is not 0, because if this was 0 this would have been identically 0, correct? So then this is not 0, and if this is not 0, this is positive definite, because why? Because this can be written as covariance matrix, so it will be positive definite. So if it is now so then this is positive definite, and if it is positive definite, its inverse is also positive definite. Okay, because of this, why? Because of u du transpose factorization. You can always invert it. So if you have u du transpose factorization, if you invert it, you will get u inverse transpose. U inverse transpose is u, then d inverse, then so you will find that again you will get a u. I mean, if you invert this matrix, then you will get another u du transpose factorization with the d matrix now as d inverse. Now d matrix is a diagonal matrix of eigenvalues. So if all the eigenvalues of d were positive, then all the eigenvalues are now going to be 1 by lambda 1, 1 by lambda 2, 1 by, they are also positive. So therefore this inverse will also be positive definite. If this is positive definite, then this is positive semi-definite. Why? Because why is it semi-definite? Why is there this possibility of it being 0? This possibility of this being 0 is because of this C matrix. Because the C matrix has now n rows and q columns. If you can see, C matrix has n rows and this n into q. So n into q means, and then n is greater than q. Generally the state dimension is greater than the measurement dimension. So it has more rows than columns, which means that it is rank deficient. So because its rank can never be more than q, but it has n rows. So therefore this itself is rank deficient. Therefore there will definitely exist some vectors y such that this will become 0. But so it will be either 0 or positive, because this is positive definite. Okay. So therefore this is non-negative definite. See, you have to, there are some little you have to go in steps, very minute details, because you cannot, mathematicians never leave any thread loose. They will tie up all the threads. Okay, that's the beauty. Nothing is left to chance. So this is non-negative definite. Fine. Then now they are also telling that even if it is non-negative definite, the trace of this will be greater than 0. Here they are not putting greater than equal to. Though this can be 0. This x transpose something can be 0. But the trace, which is the sum of all the diagonal elements, that must be greater than 0. Why? Because if the sum of this is, you can find out. I mean you can actually, we can solve some of this. If you are interested, we can solve some of this in a tutorial. It will give you some skill of manipulating matrices. It turns out that if you have this trace as, for example, now this is non-negative definite, which means that if you multiply it by y transpose this into y, it will be either 0 or positive. So let us choose one vector y as first element 1, all others 0. Using this, if we calculate y transpose this y, what shall we get? We will get that first, we will get this matrix 1 1th element. Can you follow this? If you multiply a matrix by this transpose, that is 1 0 0 transpose some matrix into 1 0 0, what do you get? You get this gets picked up, correct? So if the sum, see each of these elements are positive. So if the sum is, if this trace is greater than 0, is equal to 0, it means that each element is 0. So it means that now if you multiply by this vector, it will be, this will be equal to 0. If you next time if you multiply by 0 1 0 0, then the second element will get picked, that is also 0. So which means that this 1 0 0 0 1 0 0 0 1 0, if all these vectors, if you multiply by x transpose, rather y transpose that matrix y, it will be 0. Now these vectors form a basis, form a set of basis vectors. So that means any vector which you choose can be written as sum of these vectors, which means that for all vectors, if this is equal to 0, then for all vectors, if you multiply y transpose cy, it will be 0. That is clearly not the case. So slightly involved argument, but that is why this we can assume to be greater than 0, because this C matrix at least has some non-zero rank. If this C matrix has rank 0, then only this will be equal to 0, but that is not the case. At least there is one measurement, so its rank will be either at least 1. Okay. Now we are going to do that. So after we have proved this, now we are going to say that we can now construct. See, previously we had assumed that y hat gives me the minimum variance solution. Now I will say no. If you find such a C, then I can give you another y which will give a lower value of ft. We want to prove it by contradiction, right? So now I will construct that. Somebody actually thought it out. Somebody spent a lot of time and actually thought out that if you cleverly make this y bar like this, then so you just have to, you just have to see the trick which somebody thought out. So somebody said that okay, let's construct this y bar as this so called minimizing argument plus this one. So he has added another term. So obviously he has generated a new solution. So now he will show that this, using this, the trace, if you calculate, it is going to be less than the trace that is supposed to be given using the optimal one. But you initially, what did you assume? You assume that this is the optimal one. So this trace can never be lower than for any other estimate. That's what you assumed. So obviously your assumption was wrong. So why is your assumption wrong? Because you assume that that matrix is non-zero. So therefore if this has to be minimum, that has to be non-zero, right? So this is one side of the proof where you started assuming that is a minimizing argument, and then we will say that if it is a minimizing argument, then this must be 0. Such a thing cannot exist. It cannot be C equal to non-zero. This is one way. The other way is to start from the other way. The other way is to now suppose this is 0. Yeah. This B term is actually taken. Actually, it is very difficult to write. This B term is just this part, leaving out this C transpose, and this A term is the whole term. I just used some symbols so that I don't have to write it every time. Okay. This is just a clever way of constructing, and then they will. This is very simple. This y bar, they will put this, and then they will break it up, and then they will show that this is A, this is A, and this is A. So this is this minus A, and then A is positive. So therefore this must be less than that. Just simply decomposition. Okay. So anyway, this proof is not to line by line remember. This proof is to just reassure that it indeed comes, and to give you an exposure to a way of proving that you can prove things by this. In fact, this is a very popular way of proving things. Many theorems are proved by contradiction. Okay, either you can prove by contradiction or you can prove by construction, right? So here is a proof by construction. not contradiction. So here they will say that they will directly prove that if this condition is satisfied, now they are starting from this condition, then they will prove that for any estimate y which is not equal to this y hat, this function is going to be larger than that for y hat. Directly they will prove. So how they will prove this? So they will say that, okay, suppose y hat is, suppose y is different from y hat. In that case y tilde is not 0, it is some vector. So therefore, and obviously since y is also chosen done using some matrices of Wj and y hat is also chosen from the same space, so therefore y minus y hat can also be chosen from in this manner, just subtract these matrices. So y tilde also belongs to the same space, this y, correct, and now then simply calculate this. So again same thing, write it as y is equal to y tilde plus y hat. So and then again break it up, and it turns out that since y tilde is, see now you are using this property which you assumed. So this inner product can be written as an inner product, sum of inner products assuming with Wj, because y tilde is this. So you just substitute this thing here and then calculate the inner product. Now each of these inner products are 0 by this assumption. So therefore these two terms will go away, they will become 0 and only this will remain. Now this is obviously positive because it is the same vector square. The same vector square must be positive. So which means that this is this plus this. This one is positive, which means that this is greater than this. There is no contradiction. They will directly proving that if you assume this, you can show that for any vector for which this y tilde is non-zero, this will be more than for this directly. So it follows both ways, So this is a very, very important property, that the error, the estimation error becomes orthogonal to the measurements which have been used for generating the estimate. This is a very important quality of minimum variance estimates, okay, and that is used for generating the Kalman filter. So actually for generating the Kalman filter, because properties can become very complicated, so therefore first what they do is what is known as orthogonalization. What is orthogonalization? What they are saying is that actually you are supposed to generate, suppose these Vj's, okay. So these Vj's are the, remember that what was our Vj? Vj equal to, this was our equation, Cj xj plus eta j. So these Vj's are actually the measurements. So we are supposed to generate our estimate using the Vj's, right, okay. But rather than doing that, this will have complexity of proof. So rather than doing that, can we transform these Vj's to another equivalent set of sequence? So what they are doing is they are now defining in terms of Vj, they are defining another sequence Zj. These Zj's are called the innovations because they have a nice property, and once you have this property, you can show that, firstly you can show that estimating based on Vj's is the same as estimating based on Zj's. It is identical, because why it is identical? Because Zj's are nothing but linear transformations of Vj's. You see y hat has been generated using what? Y hat has been generated using information from V0, V1, V2 up to Vj minus 1, and here is Vj. So these Zj's have been again generated by linear transformations using V0, V1 up to Vj minus 1 here and Vj here. So they are also linear transformations of Vj. So therefore these Zj sequences are nothing but a new sequence which is generated from linear transformations of Vj. So therefore generating based on Vj's is the same as generating based on Zj's. That is the argument which is being given. But these Zj's have a nice property. What is that property? That property is that, so now, and obviously you are, what is this? This is a minimum variance estimate generated using VI's. So what they are saying is that first take the minimum variance estimate of xj, generate the minimum variance estimate of xj using Vi, then see what is Cj xj, subtract it from Vj, then you get what is known as the estimation error. Now this estimation error is called the innovation because it has certain property. What is that property? That property is that property is this. That property is that the correlation wise, now we are talking about this Z sequence which is the innovation. The property is that only ZL correlation is non-zero. For all others, Zj ZL is 0. So you have sort of made a white sequence. So again, what is this? This is the this is the estimation. This is your estimate of the output. What is your estimate of the output? The output is, suppose V is equal to Cx plus eta. You have generated x. You have got an estimate of x hat. This is totally uncorrelated with, this you have assumed that it is uncorrelated with past measurements, etc., etc. So if you have an x hat, what is the estimate of V you can generate? Obviously Cx hat. This is your estimate of V using x hat. So, but then you got V. So then V minus V hat is the error. So then V minus V hat is nothing but this Z. So it says that these Z's become white. So if you use the estimates, then the output estimation errors will become white, in the sense that their correlation functions will become Dirac delta functions. Only if it is ZL ZL it will be non-zero. If it is Zj ZL, that is J and L are different, then it will become 0. Again, number of manipulations, I am skipping them. So this is the, so what have we done in effect? What we have done is, in effect, rather than using the measurements, we have created an alternative sequence called innovations, which is linearly generatable from the measurements, but which is white. Now obviously if you deal with white sequences, all our analysis, everything will become simple. That is the advantage. And now what we are going to do is, now you see that, and then you have normalized it. Normalized it means you have found out, you have sort of scaled it. These Zj's you have scaled using this matrix. So once you have scaled them, then and you have generated this sort of normalized error, then what happens is that this correlation becomes an identity matrix. Previously it is not identity, it will have this term. So you have scaled it. So now what you are going to do is, now if you generate, now you can show that if you generate your estimate, now we want to generate a minimum variance estimate, that is our ultimate goal, that is the Kalman filter. So an alternative approach will now say that if you generate this one, so once you have defined these EIs, now so now you see that given the measurements you can generate these EIs, given the measurements you can first generate the VIs, the ZJs, and then from ZJs you can get the E's. At least recursively you can do it. So if you can generate this x hat k based on these in this fashion, now this is not a computable form. This is an abstract form. This cannot, we are not going to compute in this form. We are going to finally compute the estimate. But if the estimate, whatever form you compute, if it becomes equal to this, then we can show that it will be minimum variance. How? Because we will show that this will be 0. That is very easy to prove. So if now by your previous theorem, what did we say? That if this is my estimate, so if this is my measurement error, so if the estimation error becomes orthogonal to the measurement, all measurements, then my corresponding estimate is minimum variance, that I have just proved. So it shows that if you can generate the estimate in this form, then it is very simply shown to be 0. So therefore this is the minimum variance estimate in terms of innovations. And then I am skipping the next part. Then what they will do is that they will actually try to find a nice form, nice computing form which will be equivalent to this. That is a lot of algebra. So they will actually compute all these EIs using all the ABCD matrices, and then they will show that if you really want to compute this, you get the same Kalman filter. Actually, the Kalman filter computes this. So that is another derivation of Kalman filter. So we are not going to do the derivation, but all we wanted to say is that this is another approach of deriving the Kalman filter which uses the whiteness of the innovations property. So we want to, in that approach we want to construct a filter such that the innovations become white, and it turns out that if we can construct a filter such that the innovations are white, then we arrive at a minimum variance estimator, which is the Kalman filter. That's an alternative way of deriving it. Okay, so I am skipping all the painful other details. Now we are going to prove another one, which is this is the algebraic one. So just remember this result, that algebraically the innovations will become white, or the estimation error will become orthogonal to the measurements which is used for generating the estimate. In other words, I mean, as if it will only leave that part about which no information it is possible to extract from the measurement. See, the estimation error becomes orthogonal to the measurement. So if something is orthogonal to the, what does orthogonal mean? Orthogonal means that when are two sequences orthogonal? Right, inner product is 0. The inner product is 0 means that their covariance is 0. So their variations have no correlation. That is, sometimes this is going positive, that is going negative. And you cannot get any information of the variance of one quantity looking at the variance of the other. That is when it will become orthogonal in a statistical sense, right? So you cannot extract any further information from it. You can only extract information when two quantities are statistically correlated. If they are uncorrelated, you cannot get any information of one about the other. So now we are going to do the next one, that basically says that another way of generating the minimum variance estimate is to generate the conditional mean. That is another way. That is, other than computing, if you can compute the mean estimate of the conditional distribution, then that also is a minimum variance estimate. So you will find that, I mean, especially if you assume that all these noises are Gaussian, then you have very simple formulae for, not simple, but very nice compact formulae, such that you can estimate the conditional mean. So the conditional mean of Gaussian sequences are actually known, and the formula are very nicely given. So once you know that the minimum variance estimate is the conditional mean, you have to just estimate the conditional mean. So it turns out that also leads to the Kalman filter. So that is another pathway of leading to the Kalman filter equation. So we are looking at three ways, but they are three different concepts. Okay. So here what we are going to show is that the minimum variance estimate is actually the conditional mean. That is what we are going to see. How? So we are starting like this, that let x and y be two jointly distributed random variables, and we are just recapitulating what is the conditional mean. Basically, conditional, what does the conditional probability density say? That suppose there are two random variables, and somebody says that, okay, that random variable y took as value 2. Now, if you have this information that there are two random variables x and y, they are related in some way through their joint probability densities, and you suddenly got some information that one of the random variables took a particular value. Now obviously you can, if you knew the joint probability density, you can use this value to now calculate that the fact that I have given this information, what is the new conditional probability density function? It will get changed, right? So therefore, probability density of x will not be the same of probability density of x given y. This we had also seen in our earlier right. So and they are related by the Bayesian rule. So the conditional probability density function is actually related by this, assuming of course that Py y for a given value of y is not 0. Now what is the conditional mean? We are interested in finding the conditional mean. So what is the conditional mean? Conditional mean is just the mean according to the conditional distribution. For any distribution, what is the mean? X fx dx. So only since this is a conditional mean, we have to put the conditional distribution, right? So in this distribution, the value of y is fixed. So it becomes a pure function of, once the value of y is given, frozen at a value, then it becomes a pure function of x, right? And if you want to get the mean, you have to do the normal mean calculation only with this conditional distribution now. That is the conditional mean. Now why should it be an MVE? Why should it be a minimum variance estimate? That is what is very nice about this result. That if that x hat is an MVE, how is an MVE defined? We are defining an MVE like this. That is x minus x hat whole square. This norm means x minus x1 minus x1 hat square, basically the sum of the vector element. This is a vector norm. Given that y is equal to y, will be less than this for any other value of z. If rather than taking x hat, if you took any other value of z, the right hand side will become more than the left hand side. Now what is the right hand, what is this expectation? This expectation is over what? Expectation is, I mean, is always over something. So this expectation is over what? This expectation is over x, obviously. Because why? Because y is frozen. There is no question of expectation of y. Y is already taken a value small y. Small y is a number. Once it has taken a value, now if suppose one way is to choose x hat, another is to choose some other z. Now this x hat and z are basically functions of y. That is, given a y, you will have to define some rule by which you will have to arrive either at x hat or at z. So they are all based on value of y. If you are given one value of y, you will calculate one value of x hat. If you are given another value of y, you will obviously calculate another value of x hat. So you will have to have a rule by which you will be able to calculate x hat or z from y. So actually these are actually functions of y. So but once y is frozen, this becomes the value, and then you have to take the expectation of x, and then it will become, so the minimum variance estimate will be such a rule such that this will be minimum. Okay. Now it turns out that the conditional estimation will give minimum variance estimate. Why? So that proof is very simple. So suppose this is some estimate z. I am not necessarily saying that it is a conditional mean. Some estimate z you have calculated from y based on some rule. So obviously this norm is equal to this transpose this. What is the norm of a vector? Mane x transpose x is defined as norm of x square. Norm means, so this is equal to x1 square plus x2 square, normal Euclidean norm, length of a vector, okay, in n dimensional space. So it is x minus z transpose x minus z, this is norm of x minus z. Only thing is that you have to take its expectation, so then we take expectation with respect to the conditional distribution, because y is y. So you can just open it out. This will be x transpose x minus z transpose x minus x transpose z plus z transpose z, just term by term multiplication. So x transpose x, then then Z transpose X, actually Z transpose X and X transpose Z are same. So therefore 2 minuses and then plus Z transpose Z. Just open out the multiplication. And obviously Z transpose Z does not depend on X, it is a number. So therefore Z transpose Z will come out of the integral and you will get minus infinity to infinity Pxy xy dx, which will be 1, because the area under the distribution is 1. So therefore I have not written that integral here, that turns out to be 1. And then this is just again algebraic manipulation. You can again, you see, always if you want to prove minimization of a function, you must write it as one part which does not depend on the one part which does not depend on the thing which you want to tune for minimizing, and another part which turns out to be a square. This we have done many times in this course. So exactly I am doing this. You see, I have written it as something, one second, yeah. So this is basically, see, this is something transpose something. So this is a whole square term. This first term is whole square. Now for making it whole square, I had to include some extra terms which were not here. So I have now adjusted those terms and I have written it here. So this plus this, if you just open out and then multiply, you will get this. They are same things. Only advantage is that now this thing does not contain Z, so it is out of optimization, right? This thing is a square, which means that it will be either 0 or positive. So the minimum value it can have is 0, because it is a square. When will it be 0? When this is 0. When will it? So the minimum value of this is possible when this is 0, which means that Z is the conditional mean. This is the conditional mean. So only when Z is, so we started with some arbitrary number Z, and we found that this function will be minimized only when Z is the conditional mean. So this is another nice property, because this property is also used for deriving the Kalman filter, because it turns out that if these are assumed to be jointly Gaussian, then there is a nice formula for this conditional mean, nice formula available for the Gaussian case. So now you have to just evaluate these sigma xx, sigma xy, sigma yy, etc. for the case of the ABCD matrices, and then if you just start evaluating them and then finally make these things, you will again arrive at the Kalman filter. That's another way, but we are not deriving that. So in this class we just wanted to prove two major results of minimum variance estimators. One is that the innovation becomes white and the estimation error becomes orthogonal to the measurement. This is a very well known algebraic property which is used in several minimum variance estimators. And the second is that the conditional mean, if one can estimate, that also gives the minimum variance estimate. So with this we will conclude today's class, and in the next class we hope to see, let us see, it all depends on how I can organize, but lots of theory. So as I said that we can actually show by some numerical examples how nicely the Kalman filter works, why it is so popular, and we will have to see that, at least have some demonstration of that, numerical demonstration, which of course cannot be taken here, we have to go to another class, but we will do that. I want to show you that in some practical case, that the Kalman filter is indeed very useful.